For Halley's Comet, its slowest speed of about 13,000 meters per second occurs at a perihelion distance of 5.25 times 10 to the 12 meters. If the aphelion of Halley's Comet is 8.77 times 10 to the 10 meters, what is its fastest speed? All right, if you want to pause this video and go Google what aphelion and perihelion mean, you can feel free to go do that. Or maybe you've already taken an astronomy class and you know those terms cold. But when I looked at this question before shooting this video, I was thinking, ooh, do I remember what those were? But you can kind of figure it out from the context, even if you forgot what they were or don't know. Because it turns out perihelion is just the greatest distance. This number is larger, maybe a clue for that. Aphelion, it turns out, is the closest distance, and it also tells us that the slowest speed occurs at that largest distance, which kind of relates to what the meaning is of Kepler's second law, which we stated earlier in terms of swept out area, right? The area swept out in some time interval is constant, but kind of the logic behind that meant that if the orbiting body, when it's closer to whatever it's orbiting around, it has to move faster in order to make sure that the area swept out is going to be the same because it's that closer distance, right? It needs to kind of make up for that. And so in that sense, when it's going slowest at perihelion, that corresponds to out here, furthest distance. So if this is like the sun right here, this is maybe Halley's Comet right here. That's the perihelion distance. That's where that, so we're talking about that's where the 13,000 meters per second is the speed there. And it's at a distance of the 5.25 times 10 to the 12 meter. Aphelion, being the closest distance, corresponds to the opposite side over here. So that's where the distance is 8.77 times 10 to the 10 meter. And our question is like, well, what is the speed equal to there? That's what we'd like to look at. And again, this is the only concept we have, which makes things maybe a little bit challenging. But I think, though, that maybe one way to look at this, there's a couple ways maybe to look at this, but one way to look at this is to say that the rate of that at which that area swept out, or maybe even like, if I think about like, what if this thing moves a small distance here? I'm going to say, okay, that corresponds to like a distance delta S. And if we're at like a distance r from the sun, then I think delta A is going to be approximately equal to maybe r times delta S. Well, let's see. Is that really correct? Like, what am I thinking about here? I don't know if I want to muddle up this picture too much here, but if I say, okay, let's say here's the sun, right? Here it is here, and it's going from there to there is a distance, right? So that's the distance delta S. And we're talking about this distance. Oops, let me just make that a solid, more solid looking line there, approximately. That's the distance r, and delta A really corresponds to this area right here. So what is r times delta S? Well, r times delta S would really be the area of kind of this box here like this. So the area that's swept out should actually be equal to half of that. So maybe that would be more correct. And then if I say, okay, but what's the rate? That area per amount of time, I'm just going to make the decision to divide by delta t over here and interpret this as 1/2 r times speed. In other words, 1/2 radius times speed. And saying that that is equal to a constant, that would mean that if you're considering, say, maybe like, I don't know, like maybe if this is like R1, right, is equal to that perihelion distance, and then the slowest speed over there is V1, then this aphelion distance here, if I think about that being R2, and the question I'm trying to find, that, whoops, that should have been a 2 there, V2 is really the question I'm looking for. But based on the concept that this area swept out is equal to a constant, I think you can make the statement that comparing 2 points like that, R1 V1 must be equal to R2 V2. And since we're trying to solve for V2, I'm just going to divide both sides by R2 and get R1 over R2 times V1. And then I can just plug in all the numbers that I have here. 5.25 times 10 to the 12 meters. So this problem looked like really, really hard, but when I break this statement down in terms of like how these things should scale really in relation to each other, it becomes simpler. This is something though that I would say if you've never seen how to reason your way to an answer like this, I know I had to have someone show me. So it's definitely something worth knowing how to do, I guess. But if you couldn't figure it out without seeing it first, I wouldn't blame anybody for that. I don't think I could. Anyways, but that's the calculation I'm going to wind up doing. So I'm taking that ratio of the two distances, the perihelion and aphelion, multiplying that by 13,000 meters per second, turning to my calculator. I'm getting like 778,221.2, etc. Maybe, I don't know, is this 3 sig figs, 2 sig figs? This one's a little bit ambiguous, right? So, but maybe I'll say that it's 3 just for fun. Whoops, making all kinds of mistakes today. That should be an 8. We'll just make those last 3 zeros. So that would be a 3 significant figure answer there, which maybe that's good enough. All right, let's go and check that answer and see how it works out. Oh, what happened there? Well, I think what happened there is that the answer in the slide interpreted that 13,000 as a 2 sig fig. And my understanding from talking to chemists is that that is kind of an ambiguous case. It's not a good way of presenting a problem. And in that sense, like really both answers are correct. One just interpreted it a little bit different. I'm fortunately not picky about that in this class. And so we should all be happy about that.